Okay, so not the final review, but it's a test 1 exam review. Okay, so the things you're going to encounter on this exam are some vocabulary like intrinsic property, extrinsic property, homogeneous, heterogeneous. Pure substances, compound, chemical change, physical change. Okay, so we're going to want to understand those. What does intrinsic property mean? It's a property that is independent. Intrinsic is independent on what? It's independent on the amount, the quantity, how much there is. So what would be an example of that? Density is a good example. Density is a ratio, mass over volume, right? So if I have a big cup of water or a little cup of water, the density of the water in the big cup and the density of the water in the little cup are the same because it's just a ratio of the mass over the volume for that. Okay, so that's intrinsic. That's an intrinsic property. Okay, so if intrinsic is independent, extrinsic is what? It's dependent on the amount. So the mass of these, this one's heavier, right, than this one because this has more. So that's an extrinsic property. Mass is an extrinsic property. Volume is extrinsic. Those sorts of things. Okay. Homogeneous versus heterogeneous. What does that mean? Homogeneous means the same throughout. That means that if I take a sample at the top or at the bottom, they are the same. So if something is dissolved in this water and that thing is dissolved perfectly throughout the entire solution the same, then it's homogeneous. But if you mix it and the particles fall out or they don't dissolve, or then that would be heterogeneous because they're not perfectly the same throughout. Or if I mix two solids together, that's going to be heterogeneous because I can never mix it good enough to where it's perfectly separated. Okay, that'll be heterogeneous. Okay, pure substance versus a mixture, I guess. So pure substance, when we define pure substance, it's either an element or a compound. Okay, and that's where the confusion is because some people think that if you have H2 and O2 and H2O, and I said which one of those are pure substances, which ones are mixtures, a lot of times you choose this as a mixture, H2O, but it's not a mixture. Water is not a mixture. It's a pure substance because it is a compound. Okay? Sodium chloride is a pure substance. It's pure salt. But if you take the sodium chloride and you dissolve it in the water, now it's a mixture of two things. Okay? So I can have pure water, I can have pure sodium chloride, but if I put them together, they become a mixture. Okay? I can have pure hydrogen, I can have pure oxygen, as long as those things are apart, but once you put them together and mix them, now they're a mixture of those two gases. Okay? So that's what we mean by pure substance. So a compound is a pure substance. It's a pure substance where you've combined elements. That's a compound. Okay? Combination of 2 or more elements to form a compound. Okay, how do I identify if something has undergone a chemical change? Good. Okay. Changes its identity. If it changes its identity, it has become something different, something new. If it does that, that means it has undergone a chemical change. Now, if it doesn't undergo a chemical change, but it changes to a different state, then what kind of change is that? That's a physical change. Okay? If it retains its identity, it just simply changes in its physical state from a gas or a solid or a liquid. Then it is a physical change. Okay? It is still water, whether it's ice or liquid water. It still has the chemical composition of H2O, right? So that doesn't change. It's simply a matter of that it has undergone a physical change, not a chemical change. Okay, so basically in Chapter 1, it's mostly vocabulary that we're going to. Even though we went back to Chapter 1 already and we started doing some conversions and things like that, that'll be on the next test. Okay? So this is what you need to focus on for Chapter 1 right now. Just that. Okay? The vocabulary, words, and such. Next test, we're going to do more of the talking about the conversions, and a lot of the math will be on the next test. There's not going to be a whole lot of math here, except maybe this right here.
So we won't be doing dimensional analysis?
Not for this test. Okay? So as far as Chapter 1 goes, that's what you need to know for this test that we're doing. Okay? Now, in Chapter 2, first thing, know how to determine the number of neutrons, protons, and electrons in an atom. So if you're told that you have P32, how many protons, neutrons, and electrons are in P32? Let's start with the protons. How many protons are in phosphorus 32? How many? No, not 32. That's the mass. What makes up the mass of an atom? Two things added together. What? Protons and neutrons. So how am I going to determine the number of protons on phosphorus 32? 15. Phosphorus has an atomic number of 15. That number represents the number of protons. So there are 15 protons on phosphorus 32. How many protons would be on P31? 15 also. All phosphorus atoms have the same number of protons. That's what defines them as phosphorus. If you change the protons, you change the element. Okay? If it had 14 protons, it would be silicon, not phosphorus. Okay? So then what's the difference between P32 and P31? The number of neutrons. So it's heavier because it has more neutrons. How many neutrons are in P32? 17. So 32 minus 15, 17. There's 17 neutrons. Okay, if I subtract that 15 from 32, I get 17. There are 17 neutrons in P32. Okay? How many electrons? 15. What would I do to that atom to make it a different number of electrons? Add a charge. Would I add a positive charge or a negative charge to P32? Negative how many? 3. Phosphorus will gain 3 electrons. So it could be 3 minus. That would change the electrons from 15 to what?
18.
To 18, right? From 15 to 18. Okay. So that's how I'm going to identify the number of protons. The number of protons equals the atomic number. The number of neutrons, the mass of the isotope minus the protons. The electrons is the number of protons unless there is a charge. Then you have to subtract or add to find the charge, or the number of electrons. Okay, whether you took away or added. Okay, number 2. Know how to calculate the average atomic mass of an element. So let's just make up an example. Okay, let's just say nitrogen 14, nitrogen 15 equals 96.08%, and nitrogen 15 equals, let's just make it easier, 4.00%. Okay, so 4%, that's probably too high. Let me see. Let's do a nitrogen 13 thing. Let's just make this 3.8%, and this will equal 0.20%. Okay, let's see how that turns out. Okay, so let's say we were given these isotopes, and we were told that these are the percent abundances of these isotopes. Okay, and I want to calculate the average atomic mass from this data. Okay, first I'm going to say that the masses are 14, 15, and 13. Those are the masses of my isotopes. Okay, and then I'm going to multiply those masses by their percent abundance. The first one is 96%. Now, if I'm going to multiply something by its percent, how do I do that? I change it, right? I move this 2 places. So it's 0.9600. Okay? This is 0.0380. And the last one is 0.0020. Okay? 1, 2. So you have to move the decimal 2 places. Good. Now, go ahead, whoever has a calculator, tell me what 14 times 0.960 is, and then what 15 times 0.0380 is, and then what 13 times 0.0020 is. Okay. Okay. Say it again, the last one. Okay, so let's go ahead and add those together. What do you find? Okay, so 14.036. That's our final answer. Okay, so that's the average atomic mass. It matches closely to the one we find on the periodic table. So we can feel confident that we did it right. Okay? And so this would be how we would calculate the average atomic mass of these isotopes. Okay? Make your chart, multiply them by their percents, and then add those together. Okay? All right, so that's average atomic mass. Know what types of light make up electromagnetic radiation? Well, here they are. These are the types of light. You have radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Okay, so those are the types of things. This will be in order of energy. This has the lowest energy. Low energy. This gamma rays have high energy. What does that mean about their wavelength? If it's low energy, then what is the wavelength? Big or small? It's a big wavelength. If it's high energy, what's the wavelength? Small. Okay? And that gets us into this. Understand the properties of waves. What is a wavelength? Well, if you have a wave, the wavelength is simply measured from one point on the wave to that exact point on the adjacent wave. Okay? So this is the wavelength of this thing. Okay? That's the wavelength of that. It wouldn't matter if I measured it here. It would still be the same length. Okay? So that's the wavelength, and the frequency is how often a wavelength passes a specific point every second. So how many wavelengths pass this point right here every second? And for things that have long wavelengths, there will be less. For things that have small wavelengths, there's going to be more, which is why I have higher energy for small waves and low energy for big waves. Okay? They all travel at the speed of light. They're all traveling at the same speed, and that's how their frequency, energy, and wavelengths all compare. Okay? This is not going to be a huge part of your test, in no way. Okay? So it's not going to be a super big important part of it. Some of these other concepts will be more important, but you potentially could see something about that on there. Okay? Okay. So let's talk about the different groups found on the periodic table. So an alkaline metal is found in group 1A, the very first column of the periodic table. Helium is not an alkaline metal. It's not a metal. It's a nonmetal, so it would go over here. I'm sorry, it wouldn't go over here, but it would be a nonmetal kind of with these others. But, I'm sorry, hydrogen. I said helium, didn't I? Hydrogen is not a metal. It is a nonmetal. But there's a reason it's there, right? Because it has one valence electron. But everything under hydrogen is a metal. Lithium, sodium, potassium, rubidium, cesium, francium. Those are all alkaline metals. Okay? So those are the alkaline metals. The alkaline earth metals are right next to it. Beryllium, magnesium, calcium, strontium, barium, radium. Okay? Those are the alkaline earth metals. Those are representative metals. They represent a lot of things that you'll find or how you can calculate charges and things on the periodic table. These other ones, the transition metals, we can't do that so easily. Okay? So they're considered representative elements because we can predict their charges and such. The halogens. Halogens are right here. Group 7A. Fluorine, chlorine, bromine, iodine, antimony. Okay? Well, that's not antimony. Astatine. Okay? Antimony is like right here. Okay. So those are the halogens. That's that group, group 7A. They all have how many valence electrons? 7. They have 7. They want one more. Okay?
Do we need to know noble gases?
Okay, so noble gases would be on the end here. Okay. I can't remember if there's an actual question about that, but sure there could be.
Will we have a copy of the periodic
Yep.
table? Cool.
Mm-hmm. Okay. A family, like the noble gases or the halogens or the alkaline metals or the alkaline earth metals, are columns of the periodic table, right? Those are columns. They're families because when you look at the periodic table, they're grouped by their valence electrons. And valence electrons means that you have similar chemistry as somebody else that has the same valence electrons as you. So you're a family because your chemical reactivities are similar. Not exactly the same, but they're similar because your valence electrons are the same. Okay? Okay, how do I determine valence electrons? Valence electrons are determined by the S and the P groups of the periodic table. Okay, the very first column, how many valence electrons? 1. Second column? 2. Scandium, how many valence electrons? Uh-oh, you guys are freaking out now, huh? Okay, you're not going to have to determine the valence electrons on scandium. Okay, I mean, if you wanted to say that there's 2 of them because calcium and potassium are right in front of it, those are valence electrons. Scandium is not a valence electron, right? Scandium goes where? It goes to the 3rd energy level. It's not a valence electron. So, no. How about here? How many? 3. That's where we pick it up, right? All these guys, these don't count as valence electrons. The D elements are not valence electrons. So if you're looking at your periodic table, you can see the S and the P's are the outside. All that stuff right there, it's inside. Those are inside electrons. It's only the S and P's. 1, 2, 3, 4, 5, 6, 7, 8. Those are my valence electrons. That's how I count valence electrons. Okay? Okay, be able to predict an ion from the periodic table. So what is the charge of an ion from elements found in the first column of the periodic table? What is their charge? +1. What about from the second column? +2. What is the charge of an iron? Now you guys are like, oh, we know you now, Mr. Crandall. Right? We don't know. We don't know what it is, right? We cannot predict it from the periodic table. So if I need to know the charge of iron, I have to figure it out from the compound that it's with, what it's in, or from the name. That's the only way that I can figure out the charge of an iron. Okay? What about zinc? 2+. You need to know that one, right? Because it's one that is always the same. How about this one? 2+ also. How about this one? +1. How about this one?
The name will tell us.
The name tells you, or the compound tells you. Okay? Those are the only 3, right? Just those 3 right there. Those are the ones that I need to know because the name won't tell me. Maybe the compound would, but if I just had the name, it wouldn't tell me. Okay? So it's 2+, 2+, 1+. Those are the 3 that you need to know. Okay? What's the charge of Al? 3+. It has 3 valence electrons. It is a metal. Because it's a metal, it's going to lose valence electrons. Boron, it's a nonmetal, but it is not going to gain 5. It's not going to become ionic. So don't worry about it. It's not going to gain 5 electrons. Okay? It's not going to do that. So boron isn't one that you have to worry about. You don't need to predict the charge of boron or even of carbon. But these nonmetals right in here, I do. Nitrogen, what's the charge? negative 3. 1, 2, 3. It has 5 valence electrons. It wants 8. So it's N3 minus. Oxygen, O2 minus. Fluorine, minus 1. Chlorine, bromine. Okay. So these guys are all minus 1. These are minus 2. These are minus 3. Okay? That's what I'm predicting. This red line divides the nonmetals from the metals. The metals don't lose electrons. What's the charge of this tin, number 50? It's a metal. Is it going to gain 4 electrons? No. It's a metal, so what does it do? Loses electrons. Loses electrons. What's the charge of that tin? I'm sorry, yeah, tin. What is it? It could be, but I'm not sure. You have to look at the name. Okay? Because to lose valence electrons, what does tin have to do? It has to go through all these. Okay? So maybe it will lose 4. Maybe it'll only lose 2. Okay? So you have to look at the name, and when I name tin, I have to state what the charge of tin is in my compound. Okay, let's see where we're at. The definition of isoelectric. So if I have an ion like O2 minus, what other elements are isoelectric to O2 minus? Okay, neon. What else? What does isoelectric mean? It has the same electron configuration. What is the electron configuration of O2 minus? 1s2, 2s2, 2p6. What else has that same electron configuration? O2 minus, neon, what else? What is it? Fluorine what? Not fluorine on its own. That would be 2p5. Negative 1. F minus. What else? N3 minus. What else? Na plus. What else? Those are all isoelectric with each other. Okay? What is isoelectric with krypton? Br negative 1. What is it? Se2 minus. Rubidium plus, strontium 2 plus. I'll take one more. As3 minus. Okay? So these are all isoelectric with krypton. They all have the same electron configuration. Okay? So don't just think isoelectric means you have the electron configuration of the noble gas. It could be between these two things or between these two things. Those are isoelectric with each other. Okay? Neon might not even be an answer choice. So you need to be able to find the other thing that is isoelectric. Okay? All right. Okay, we already did that. Number 11 is kind of a repeat. Principal and sub-energy levels. Okay? How do I identify the principal energy level of an element. Let's take phosphorus. What is its principal energy level? Is it in principal energy level 1, 2, 3, 4, 5, 6, or 7? Phosphorus is in 3. This is the third period, right? Phosphorus is in the third energy level. What sub-energy level is phosphorus in? P. What principal and sub-energy level is strontium in? Five S, right? What principal energy level and sub-energy level is silver in? Four D. Because this is the 3D, right? This is the 4D. So silver is in 4D. It's in 4D. Okay? What principal and sub-energy level is uranium number 92 here in? 5F. Excellent. Okay? It's in the 5F. Okay, so if I have a periodic table, I can label it. I can identify everything on it. Here's my periodic table, okay? And if I just label the first thing in each group, it will tell me where everything resides. 1, 2, 3, 4. That's it. That's all I have to do. Label it 1, 2, 3, 4, and then I know where everything is. What sub-energy level is number 1 in? 1s. What is number 2 in? 2p. 3 in? 3d. 4? 4f. So that is the first of its group. And then I can just label down 1s, 2s, 3s, 4s, 5s, 6s, 7s. 2p, 3p, 4p, 5p, 6p, 7p. 3d, 4d, 5d, 6d. 4f, 5f. Okay? Now I can keep myself straight on where everything goes. Okay? Because I have identified it on my periodic table. Exactly where everything goes. 1s1, 1s2. 2s1, 2s2, 2p1, etc. 2p2. Now I can start to write electron configurations. Okay? 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And that's how I identify where the elements are on the periodic table for their electron configuration. Okay, so know how to determine an electron configuration. How do I write an electron configuration? Let's do it for cobalt first. Okay, what is the electron configuration of cobalt? How do I start? 1s with hydrogen, right? And I will fill it because I'll go all the way to helium. So it will be 1s2. Okay? Where do I go after that? 2s. Where do I go after the 2s? 2p. Now where? And now? Next? 4s. I simply reading, right? When I get to the end of the 3p, where am I? I'm right here. Number 18, argon. That's the 3p, right? Now I go 4s. What comes after the 4s? That's right. 3d. Now where does cobalt reside in the 3d? 7. Okay? So 7. Everything else that came before is full. 6, 2, 6, 2, 2. Okay? This is my electron configuration for cobalt. My electron configuration. Okay? Yes? It depends on what the question says. If it says that you can, then go ahead. But if it says it has to be in longhand, then write it in, enter it in longhand. Okay? Because you're not going to turn this into me to be graded. It's going to be graded by the computer. So you have to do it in the format that it tells you, so it understands what you're doing. Okay? All right. But if it was shorthand, then we would simply go to the argon, the noble gas, right? Cobalt equals argon, brackets, 4s2, 3d7. And we write like that. All right? Okay. Okay, how about the trends? How do I identify the trends of the periodic table? So my trends start here with fluorine. So if I am going to identify atomic size, and I start with fluorine, then I need to understand that fluorine is what? Big or small? Small. Fluorine is small. Okay? As I move away from fluorine, what's happening to my atomic size? It's increasing. You move across or you move down, it's going to get bigger. Okay? My atomic size is increasing as I move away from fluorine. So that's the first trend that I want to try to understand. Okay? For all the other ones, so ionization energy, electron affinity. The trend starts here with fluorine, and it has a large electron affinity, a large ionization energy. And as I move across this period, what's going to happen to that ionization energy? It's going to decrease. As I move down, the ionization energy is going to decrease. As I move across my periodic table, it will decrease. Okay? So you start with fluorine, and that's the trend. That's the trend that I would follow for ionization energy and electron affinity and even electronegativity. Okay? Now, for the size of an ion, okay, ion size, it's a little different. Okay, so if I want to know which one's bigger, N3 minus or O2 minus, okay, how am I going to determine it? How will I determine the difference in the size of those? Which one's bigger? Okay, figure out the number of protons versus the number of neutrons. How many protons are in nitrogen? How many, sorry, not neutrons. How many electrons are in nitrogen? 3 minus. 10. How many protons are in an oxygen? How many electrons? So they both have 10 electrons. One has more protons. Which one will be smaller? The one with more protons or less protons is going to be smaller. More protons. Why? Remember, chemistry is all backwards. Why is it that if I have more protons, my atomic size is smaller?
It holds everything in.
Because what determines the atomic size is my electrons. I have the same number of electrons on each of these, right? And they're spread out. More protons means what? I pull them closer. More protons means I pull them closer. The nucleus is a very tiny, dense region. It's the electron cloud that determines the size of my atom. So if I can pull my electrons in tight, then I will have a smaller atomic size. So it is the number of protons that determines the atomic size. So oxygen will be smaller than nitrogen as an ion. Okay? So what is the atomic size? Which one is smaller, lithium plus or beryllium 2 plus? Okay, so we have protons and electrons, protons and electrons. Lithium has how many protons if it's, if it's a lithium, how many protons does it have? 3. Beryllium has how many protons? 4. As ions, they both have how many electrons? Lithium had 3 protons. It lost 1. Now it has 2. Beryllium had 4. It lost 2. It now has 2. So, which one's smaller? Beryllium. It has more protons, right? More protons means I pull those electrons in tight. Okay? So, more protons, I'm pulling my electrons in very tight. They both have the same number of electrons, but beryllium pulls them in tighter. Okay. Okay, and be able to define ionization energy, electron affinity, and electronegativity. So ionization energy is the energy required to remove an electron from an element. So fluorine has a high ionization energy because it doesn't want to give up electrons. Fluorine doesn't give away electrons. What gives away electrons? Metals. So metals give away electrons. They have low ionization energies because they will give away their electrons. But things that have high ionization energies, like the nonmetals, they won't give away their electrons easily. You will require a lot of energy to pull an electron off of fluorine because it has a strong hold on its electrons. Okay, so electron affinity is the energy released when an electron is bound to an element. So if you bind an electron to a metal, it doesn't like that. It doesn't want electrons. It doesn't want more electrons. It wants to get rid of electrons. So if you bind an electron to a metal, then it releases low energy because it doesn't want it. It doesn't want that electron. But if you bind an electron to fluorine, it likes that. It wants that electron, so it's going to release a lot of energy. So it has a high electron affinity, meaning it has a strong attraction for electrons. Okay? It gives away electrons, not very easily, but it has a strong attraction for them, so it picks them up well. Electronegativity is the pull for electrons that you have. Fluorine has a strong pull for electrons, and so that electronegativity is what determines polarity in a lot of these molecules. Okay? All right, so Lewis dot structures of elements. So if I'm going to determine the Lewis dot structure of an element, okay, then something like magnesium would have 2 valence electrons. That's its Lewis dot structure. Magnesium 2 plus would have no electrons around it because it would lose its valence electrons. Nitrogen would have 1, 2, 3, 4, 5 valence electrons. And 3 minus would have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It would have 8 valence electrons to finish its octet. Okay? So that's the dot structure of just the elements. Okay? And that's what it means there. Know how to name ionic and covalent compounds. Okay, so I think you guys need to focus a lot on this because I think this is where you could struggle, being able to name these. And I gave you that big packet, right? Make sure you're going over that. Make sure you understand how to name those things. I put the key online so that you can check yourself. Okay, so make sure that you're getting that down. Let's do a few examples. Okay. What is the name of this compound? Okay. Now, why don't I say dichloride? Because it is not covalent. How do you know it's not covalent? It starts with a metal. So it starts with a metal. So it's ionic. So I have to use the rules for naming something that's ionic. Why don't I need to say dichloride? Is magnesium dichloride probably going to be an answer choice? Yeah, probably. So make sure you know not to do that. Why don't I say magnesium dichloride? Why is it that ionic compounds do not need you to say how many there are? It's because they come together based on what? Why did I need 2 chlorines? Because of their charges. So they come together by their charges. Right? So if I know their charges, then I know the formula. So that's why you don't have to tell me how many there are if it's ionic. Okay, so if it's ionic, don't tell me. When do you use prefixes? When it's covalent. Only when it's covalent. Okay? So, if it's covalent, yes, use prefixes. But if it's ionic, they can only come together in one ratio. And you can figure that out from the charges. If it's covalent, they can come together in hundreds of different combinations. And so you have to tell me how many of each thing there is. Okay? That's the difference between naming something that is ionic and something that is covalent. Covalent molecules, you tell me how many. Ionic compounds, you never tell me how many. Okay? What's the name of this compound? Fe is iron. Okay, so it's iron 2 oxide. You think iron 1 would be an answer choice? Probably. Why is it not iron 1? Why is it iron 2? Because oxygen has a -2 charge, so iron has a +2 charge. Okay? So, no subscripts. What do you need to be careful of? It doesn't work, right? Don't switch back if there's no subscripts. If there are no subscripts, be careful. If there's only one subscript, be careful. Let's see. Let's do this. That's manganese. Not 2. 4. Manganese 4 oxide. This did not work, right? One subscript, be careful. No subscripts, be careful. One subscript, be careful. When does it work? How many subscripts do I need? You need 2. If you have 2 subscripts, it's going to work every time to go backwards. Okay? So, what's the name of this one? Iron 3. It works to go back when I have 2 subscripts. If I only have 1 or 0, be careful. 1 sometimes works. You want to know when it works with you have 1? When it's on the metal. If it's on the non-metal, it doesn't work. If it's on the metal, it will work. Okay? So you need to be careful of that, of my subscripts. Okay? So it doesn't always work to go backwards. You got to figure those out sometimes. Okay? If you have 2, it's golden, right? It works. So you'll be like, please give me 2. Computer, it's picking out of all these ones. You're like, give me the ones with 2 subscripts. Okay? So you don't know. You might get one of these. You might get one of these. You might get one of these. So you need to know how to name all of those. Yes?
How did you get manganese 4 again?
Manganese 4? Okay? It's because this oxygen has a -2 charge on it, right? But there's 2 of them. So overall, the charges from the oxygen are -4. There's only 1 manganese, so if I distribute that 4 negative to the positive charges of the manganese, it becomes 4 plus. So it's manganese 4 oxide. Okay? And then somebody else had a question. Oh, okay. Same question. All right, great. Two for 1. Okay. So, what's the name of this? Phosphorus trichloride. So easy. So easy. That's how you want to name everything, and you can't. Okay? So, don't use prefixes for these ones, for the ionic ones. Phosphorus trichloride. Gosh. Okay? So, that's how you're going to name those. All right, where are we? Let's see. What is the formula for this? Ca what? 3 and 2. Okay? Calcium 2 plus and 3 minus. That means I need 3 calciums and I need 2 nitrogens. Okay? In my formula. So my formula is Ca3N2. Yes?
Do you want us to know which are polyatomic ions?
I don't want you to memorize them. I will give you a chart of those, but you will need to know how to use them. And let's do a few examples of those, okay? Okay, carbonate, you would find that on your polyatomic ion chart, CO3 2 minus. What is the formula for this? K2 CO3. Okay, so this is K positive plus 1. So I will need 2 of them, and I will only need 1 carbonate. Okay? What is the formula for magnesium phosphate? Phosphate is PO4 3 minus. Okay, brackets, PO4, I need 2 of them. So Mg is 2 plus, so that means I need 3 magnesiums and I need 2 phosphates. Okay, for this formula. That's how I'm going to determine that. Okay. What is the name of that compound? Yeah. Sodium sulfite. So don't get tricked that it's sulfate. Look it up on your chart. Okay, sulfate is SO4. So this is SO3. That's sulfite. Sodium sulfite. Okay, so don't be tricked by that. Don't just assume it's sulfate. Find it, look it up. What's the name of this? Is it covalent or ionic? It's ionic. Ammonium is a polyatomic ion. Nitrate is a polyatomic ion. Those are both covalent ions. So when they come together in ionic combination. That means I don't use prefixes. This is not nitrogen, tetrahydride, mononitrate, nitride, trioxide, okay? Or whatever combination you could think of, okay? It's not that. It's not covalent. This is an ionic compound. Ammonium nitrate. Done. It's ammonium nitrate. Here's your ammonium. Here's your nitrate. Okay? There are more than 2 elements in this compound. Therefore, I know there's a polyatomic ion, which means this must be ionic. Okay? Even though it starts with a nonmetal. But that's the only time you'll see a nonmetal at the beginning, is with ammonium. That's the only time you might be tricked. But don't let it trick you. If there's more than 2 elements, there must be a polyatomic ion. Okay? And you just find that polyatomic ion. Okay. Now, let's go over how to draw structures, because that's another big part of what you'll do. Okay? What is the structure for carbonate? So first, I write the number of valence electrons. Oxygen has how many valence electrons? Carbon has 4. Oxygen has how many? 6. 6 times 3, we have 18. Plus 4, 22. But what does that negative 2 mean? Not lost, gained 2 electrons. So add 2 more, 24 electrons in my structure. Carbon surrounded by 3 oxygens. I start everything out with 8 valence electrons. Okay? How many electrons are in that structure as I have it drawn right now? I think I heard it. Somebody said 26. There are 26. I don't want 26. I want 24. So what do I need to do to get from 26 to 24?
Make a bond.
Make a bond. The only way you can remove electrons is by making a bond. Now I'm at 28. I have to take electrons from both of the things I bonded to. I have to take a pair of electrons away from both of the things that I bonded to so that I can maintain the rule of 8. 2, 4, 6, 8. 2, 4, 6, 8. Both of them have 8 electrons around them. Okay? They have to. That is a requirement to show that you have drawn your structure correctly. Okay? Let's try another one. Carbon dioxide. Carbon 4, O2 is 12. That's 16 electrons. Carbon with 2 oxygens around it. Start everything out with 8 electrons on it. That's how you always start everything, with 8 electrons around it. I want 16. How many electrons are in my structure? 20. What am I going to do? Make a bond. Remove electrons from here and here. That reduces the number by 2. So I went from 20 to 18. That's still too many. Now what do I do? Make another bond. Remove electrons. Now I'm at 16. This is my structure. Okay? I'm at 16 electrons. Everything's following the rule of 8. 2, 4, 6, 8 on the oxygen. 2, 4, 6, 8 on the carbon. 2, 4, 6, 8 on the other oxygen. Everything's following the rule of 8. I have 16 electrons in my structure. Therefore, this is my structure. That is my structure.
We can have any of those exceptions, like hydrogen.
Okay? So if you have some, what about this one? So total valence electrons B, 3, Cl, 7 times 3, 21, 24 electrons in my structure altogether, right? Okay, so boron is in the middle, surrounded by 3 chlorines. Okay, is this how I start?
No. Going from number 3.
There's 26. I want how many? 24. So what do? Okay, make a bond. Remove electrons. This is the most common structure that I see. And guess what? It's absolutely wrong. What's wrong about it? I did everything right. Everything's following the rule of 8, etc., etc. What's wrong about it? Boron doesn't follow the rule of 8. Look where it is on the periodic table. It comes before who? Carbon. Only after carbon do I follow the rule of 8. Everything before it does not follow the rule of 8. You can't. It doesn't have enough electrons. It only has 3 valence electrons. So boron does not start out with 8 electrons around it. Instead, this is how you start that structure out. Okay? This is how I start it. Without the other 2 electrons here, it will not follow the rule of 8. This is my structure for boron trichloride. Okay? Don't be tricked by that. That's one that comes up a lot. That one right there. Okay? So make sure you know that that is an exception to the rule of 8. Okay? NH4 plus. Nitrogen has 5. H4, that's 4. 4 plus 5, 9. But it's a positive, so it's minus 1. And I get 8. 8 electrons. Nitrogen, hydrogen, 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 hydrogen.
Hydrogen can't have that many.
Can't. I can't do this, right? I can't do this, but I see it all the time. Okay? Hydrogen cannot have 8 electrons, right? Because it comes before who? Carbon. So it's an exception. How many electrons can carbon have around it total? Just 2, which is what? 1 single bond. That's it. So I don't start hydrogen out like that. I start it out like this. Okay? And there's my structure. That's my structure right there. Okay? It has a positive 1 charge on it. Okay? That's my structure. Okay. Really quickly. Boiling and melting points. Okay? Okay, so I have these. I want to arrange them by boiling and melting point. Oh, let me throw this one on there. Okay, which one goes to the very top? Ionic compounds. Ionic compounds are first. Do I have an ionic compound here? NaCl. The next group is the polar group. Okay? Now, what goes to the top of the polar group? Things that hydrogen bond. Does anything hydrogen bond here? Water. Because it is either nitrogen, fluorine, or oxygen bonded to a hydrogen. Therefore, it will hydrogen bond. It goes to the top of the group. What goes next? What other two things are polar? Or what else is polar? PCl3, SO2. Those are polar. Okay? These other things, H2, carbon dioxide, methane, and I'm sorry, not H2O. H2 carbon dioxide and methane are nonpolar. So these are my polar molecules. We already took care of water, so I'm left with PCl3 and SO2. Which one's heavier? PCl3, so it goes above SO2 because it's heavier. Now I have nonpolar. Which one's first? Carbon dioxide is the heaviest, then methane, and then hydrogen's the lightest of them all. Okay? All right, so that's how I'm going to arrange predictively my boiling and melting points. Okay?